Okay, so moving ahead now. So we know that these electrons are able to diffuse and diffusion current is more. So see here, we'll discuss this later on. But under this no biasing condition, when we don't connect a battery here, then the net current is equal to the diffusion current minus drift current, both are equal to I naught. But we know that now in forward biasing, this the diffusion current is increasing exponentially with the applied voltage. So the expression after derivation, there is some semiconductor theory, we don't have that in our syllabus, but then this diffusion current comes out to be like this. So this V is the applied voltage here, V is the applied uh, forward potential difference, so we can say that applied voltage. So initially, as you can see, when the applied voltage is 0, so this term becomes 1, and so the net current is 0. But as we keep increasing the applied voltage, this diffusion current increases exponentially, whereas the drift current remains same. So if we plot here, so if you see here, this K is the Boltzmann constant, and T is the temperature. So at room temperature, which means at 300 Kelvin, and the Boltzmann constant to be like 1.38 into 10 is obviously you know that. So KT in electron volt comes out with this, and let's consider the I naught, which is the general value roughly around 10 microampere. Well, it depends on some factors, for example doping concentration and everything, but let's say that in a special case, so I naught is 10 microampere. So if we substitute this 10 microampere here in the expression, so this I naught and e raised to ev by kt minus 1. So when we keep on substituting the different values of potential difference applied, and obviously the values of k and t and everything else, and e raised to obviously, so what we get is I. So when V is 0, the current is 0, the net current. Whereas let's say if this is the applied voltage, is 0.05 volt only, it's 46 microampere. If you double, it becomes almost 10 times. If you double again it shoots up like anything. What about 0.3 volt, around 1 ampere? And when if we increase all the way up to around 0.7 volt, remember that in case of 0.7 volt forward potential difference, and the barrier potential was also initially 0.7, so the forward potential difference and the already existing barrier potential difference, they actually cancel out each other. So the barrier height is effectively 0 at 0.7 volt, and the current will come out using this formula to be around 4.9 million amperes. That's tremendously high. So if we plot here the IV characteristics of the diode in the forward biased, so initially we get a very small current. If you see here, so for very small voltages like 0.05 or 0.1, so the current is in the microampere region, whereas when we make it almost up till a 0.7 volt, the current becomes extremely high. So that is what is the IV characteristics of a forward biased. So this current to be significant, we say that the potential difference that should be applied should be roughly around 0.7. So that is what is called as the cut-in voltage. So prior to this voltage, the current through the diode is very less, and once the voltage across the diode becomes around 0.7, then the diode can conduct extremely huge amount of current, and so we say the diode becomes conducting here. Okay. So there are a few more things about the forward biased here characteristics. Okay, so we came to know that the electrons can diffuse from n side to p side like this, and there is a diffusion current here. So what does the battery do? Well, if you see a normal conductor, isn't it? So when we apply a potential difference across this normal conductor, we know that the current starts to flow like this. Why the current starts to flow? That's because of the electric field of the battery. Now these electrons, they get a force opposite to this electric field here. So electric field of the battery is like this, and the force on the electrons is like this. Because of this force, these electrons move backward, and we call this phenomenon to be drift, isn't it? So electrons are different here like this. So what battery does is, it takes these electrons from here and dump it on this side, and the electrons again they come here, and then again battery takes them out and again dumps them on this side. So this is how the anti-clockwise motion of the electrons is there, and because of the anti-clockwise motion of the electrons, there is a clockwise current opposite to the negatively charged ions movement. Okay. Now, so yeah, one or two more things. What happens to the width of the depletion region here? Well, it is decreased in the forward bias condition. So we have here a PN junction which is like forward bias obviously, and you can see that there is some small amount of electric field applied here. So this is the E applied by the battery here, of the battery, and this is of the battery. So let's consider first the N type. So as the electric field is applied here, obviously the electrons will get some force like this in this direction, isn't it? And these electrons will start to move like this. And these electrons, while moving like this, these electrons will come here and they will cancel out this positive charge somewhat. And so these positive charges are bound by the electrons which are moved here. And since electrons, the external electric field is like this, and we know that there are lots and lots of holes here. And all of these holes are positively charged. So the holes are positively charged, so these holes will move here and they will consume these electrons. So positively charged holes and negatively charged boron, both of them together make a neutral. So this will also become neutral and this will also become neutral. So the width of the depletion region is decreased in the case of forward biasing. If you don't understand the movement of holes, we can understand it with the help of the movement of electrons in the valence band also. So let's say this is a silicon mesh on the p side. Alright, the two-dimensional